right. First and foremost, RTFQ, then ATFQ. I can't emphasize that enough. No, they can figure it out. All right, now reading the question. Now listen, reading the question, you will get the right on your test form. And I know I've said this numerous times. Box in information, underline information. I am 99% sure you may not bring in highlighters. Okay?
It's illegal, you can't.
I didn't think you could, but you can bring in pencils and pens. You can bring in colored pens. You can bring in, no, I'm not going to say colored pencils.
Markers?
No markers, no highlighters. Okay, so you can bring in pencils and pens. Also, and I know some of you are uncomfortable with this, but on the free response, you may use a pen. It might be a little easier for you guys and a little smoother to write with. If you make a mistake on something that you've written, simply just cross it off.
What about scribble?
Don't scribble, just cross it off. Also, do me another big favor, that if you, like, this is your initial answer, and then you say, no, I meant to write ATFQ. Now listen, if you write down two things, and you meant for this to be graded, and you left that there, that's going to get graded, that won't. So that would make this nullified, so you want to strike it out.
Can you like circle your answer?
You can circle it, yes.
They take the most wrong answer. Or the one
They don't take the most wrong answers, they take the first.
Oh, really?
Yeah, so if you do a bunch of work here and then you go, oh, no, that's not right. And some of you like to copy because there's one thing, or at least if you said, okay, that word I didn't want in there, I wanted that to be facts instead, then you can draw an arrow to that. Okay? Just saying. That's instead of having to rewrite all of that. Okay? All right. Let me go over, and again, I'm just going to hit some highlights based on things that I've heard. So hopefully I'm not going to read all this to you, but there were a couple questions that were on your mock exam, and again, I like those questions because I have a very strong feeling you're going to see something like that again, just reworded, the names will change, the people will change. At equilibrium, the rate of the products is equal to the rate of, the rate of the reactants forming products is equal to the rate in which the products are forming the reactants. Somebody asked today, the initial rate, in other words, you start with reactants and no products. When is the rate fastest for a reaction that's undergoing equilibrium or going to equilibrium? The initial. So the initial rate is the fastest that reaction will go. It'll eventually slow down. Now, normally we don't talk about equilibrium in terms of rates, but there was a question on the mock that asked about rates. So what it's going to do is actually start fastest at the beginning, and then as it reaches equilibrium, the rates of which the forward and the reverse will then become equal.
But not zero.
But not zero. They won't stop. Yeah, they shouldn't stop, but that's not equilibrium. So that was one thing. Make sure that you understand Le Chatelier. Okay? It is very easy. The only time that K changes, the equilibrium constant changes, is when the temperature changes. Or when you have partial pressures and the same number of particles on both sides. And I had that somewhere in here. So normally they'll give you like one particle over here and two particles over here that are gases. That, the K won't change. And that's the KP. So if you're using KP, make sure that you use parentheses if you're writing the expression. Make sure you know what side endothermic, exothermic is on. Oh, here's something. An interesting fact. When a system in equilibrium has a reactant or a product added to the reaction or stress is imposed, its concentration or partial pressure will be greater when it's at equilibrium. Once equilibrium is reestablished because we've added something to it, that pressure or that concentration will actually be higher than it was at equilibrium. And that was one of the questions that Sam and I talked about this morning. I thought that was a really good question. So in other words, I can't remember what question number that was, but they did something like this, where you're at it's equilibrium, and then it's at equilibrium, so it's flat. And then they added something that spiked, and it did this. And then they compared that to another graph that looks something like this, where it started and it spiked and it went lower. So what's happening is the concentration after this thing was added was actually lower. Well, that's not going to happen. What's going to happen is, if it takes, say, in the reaction, there is, let's say there's A and B that's actually formed. Should move that over. Okay, and it's making C. If I add more B, what happens to the concentration of A? Goes down. So it's going to be lower than its initial concentration once equilibrium is reestablished. But if I add more B, then its concentration goes higher, and I'm not going to use as much, but it's going to actually be a lot higher, or not a lot higher, but it'll be higher than the concentration it was initially at equilibrium. And this is supposed to be a flat line like that one. So that was just another thing that I was like, oh yeah, that makes sense. You should get a graph to help you look at that.
Wait, Craig, so that graph is representing B?
This would represent B, yes.
And if it's lower, it's A.
And A would be lower. So A's graph would look something like this. It would be at equilibrium, and then it would drop down. So I think there was a graph that looked like that on your sheet.
So it wouldn't have a spike?
Wait, Mr. Craig, you mean A
No.
or C?
This is A, and this is B. Okay? So it's at equilibrium because, again, when we add more B, it shifts away from the addition. So we spike that concentration of B, and then equilibrium is reestablished because we're going to take some B, hook it up with A, and make some
I thought
C.
you meant if you're adding
So
more A.
A is going to go down as a result of this. And I think that was one of the graphs on the question as well.
So for C,
C's just going to, C will look like,
reverse of A.
it'll look like this. So we're at equilibrium, and then it'll start to go up. Something like that. So its concentration will
But
increase.
that's C?
That would be C, yes. So it'll actually increase a little bit, and then level off. All right. And then there was another question about completion.
Yeah, that one was weird.
That it was, and Sam and I actually argued about it for a while this morning, and then we finally read it, or I finally read it. Do equilibrium reactions go to completion?
No.
No. So when you read a question that says it's going to completion, it's no longer equilibrium. All right. So if it's going to completion, focus only on the products, which I think is a BS question. I don't like it. Because if it's at equilibrium, it's highly unlikely that it's going to do that. All right, but I'm not writing the question. Quick facts about Q, so make sure you know those. Now, here is just the typical equilibrium curve, graph, whatever. Conductivity got me thinking. I was like, okay, I wouldn't be surprised to either see a concept question or another free response question dealing with conductivity. One thing about conductivity is we don't care about pH. Okay, so whenever it's doing something like that, look at your information there. This is what a typical setup would be. And I had a student about 8 or 9 years ago, like the second year I was teaching AP, came back. He was taking chemistry at Rose Holman. He said, "Oh yeah, that's the only way we do our titrations." I was like, "Who does that?" Rose Holman, got it. And he said, "You can determine the equivalence point." They had lights on, they had the electricity turned on, the circuits were all plugged in. When it gets to the equivalence point, it looks like the big favorite is sulfuric acid and barium hydroxide. And again, you got to realize that there's not a lot of things out there that would be forming a precipitate. So if you're looking at conductivity, we don't care about pH. We care about when the acid is equal to the base. So we're going to form a precipitate. We have to be forming a precipitate. And we also have to be forming what? It's an acid with a base. Water. So water is going to be formed. Pure water does not conduct electricity. Pure solids, or PPTs, don't conduct electricity in a solution because where does the PPT go? It goes right to the bottom. So those electrodes aren't touching that. Now, true, there are some solids that do conduct electricity, but not in solutions. All right. So when looking at this set of data that I found, it says, all right, we have 25 milliliters of sulfuric acid in the beaker to begin with. The volume of the barium hydroxide is added. At 26.7 milliliters, the lamp goes out. What can you say about that? At 26, when you've added 26.7 milliliters of barium hydroxide, you are at the equivalence point. All right, so it's just like on the mock exam where that dip was, whatever that was. Okay, so the conductivity or the ability for the ions to help relay those electrons from that electrode to that electrode has been taken out because we have pure water and a PPT. And then as we add more of the barium hydroxide, then the lowest current reading, and then it starts to turn pink. What does pink mean again?
Indicator.
It's an indicator, and it's phenolphthalein, and it tells us that we're getting on a basic side of this pH. So that might be the only way that we're going to be able to determine the pH. And then say as the lamp goes on, that means we have enough ions in solution. What are the ions that are in the solution? Let me ask you that. Once the light comes back on, actually let's not use that color. What are the ions that are present when the light comes back on? Ba plus 2?
OH negative.
And OH. Okay? So if we have reached the equivalence point, how much of the hydrogen do we have left? None. It's gone. Also, the sulfate that came in the package, how much of that sulfate do we have floating around in the solution? None. It's all reacted with the barium to get to the equivalence point. So all we're doing is we're adding more barium ions and hydroxide ions. So we're just flooding the system with those. So make sure that the equivalence point, you know that the thing you started with is gone. All right?
Forever?
It's gone.
Forever?
Yeah. As long as forever can be. Yeah.
Can you go back to the thing where it just takes the volume pressure? Why would,
Where's that? Back here?
yeah, pressure, why would it change if it has the same number of gas particles?
Okay, so here's what you're saying. So I've got two A's that make two B's. Okay. And let's say that I have my volume that goes from here to here. So as the volume gets smaller, what happens to the gas particles inside that container? They start colliding more often. So the pressures go up. If there's no way for me to counteract that by saying a normal equation where, okay, on this side, if we have two gas particles and here we have one gas particle, we can reduce the pressure by reducing the number of gas particles present. And that's what happens. The reaction would actually shift to the right here because here we have two particles, here we have one. This is going to reduce the overall pressure. So that's a good thing. But if there's two on each side, there's no way for those pressures to be adjusted, so your K will change. And also, as a result, your temperature should change as well. Yeah, good question. All right. Let's see. Acids and bases. All right, what I have at the very beginning here is make sure you can determine hydrogen concentration and pH without a calculator. You'll see at least one, if not two, of those types of questions on the multiple choice. Now, on the free response, use your calculator, have fun. But here what I have are some examples of how to do logs in your head, or actually get some ballpark figures of some log values or anti-log values in your head. Also, what is not given on your calculator is that, okay? Going from concentration to pH or POH. Those are not given while this is popping up here.
So the fourth example right here that says a 4.33
Okay.
is going to have a pH between 7 and 8.
Mm-hmm.
I've seen this in problems like on the multiple choice, and they say because it has a pH of this, then like what's the concentration?
Yes.
And it gives you numbers that aren't like 1.0, like it gives you other numbers like that 4.3. So
Beautiful.
How do you tell when it's those type of numbers that aren't just straightforward numbers?
Okay, so let me minimize. Whoop, wrong one. Hang on. All right, so like you're saying, they're giving you pHs and they want to know what the concentration is. Okay, so let's say that you're given, say, a value of 5.88, just as a pH. So you know that concentration for the hydrogen has to be somewhere between 1.0 times 10 to the negative 5 and what? In other words, we're going from 5 to 6 to negative 6. Okay? So, or wait. Yeah, we're moving in that direction. So your answer would be somewhere in there. That's the best way to do it.
But
What?
they're not, but they don't, the multiple choice options are not 1.0 times.
Correct. So your option is going to be between here. So what they're not going to do is they're not going to give you two answers that are in here.
What if they give you like a 3 point? Yeah, they're going to give you something like 3 point something.
So let me ask you this. If, say, they gave you, I don't know, 4.55
Yeah.
times 10 to the negative 6, is that
Yeah.
in there?
Something like that.
6 and 7.
No, I'm saying, would that be an option in between those?
Yeah.
No.
That's not an option between those two?
Oh, yes, it is.
Yeah.
How do you?
How do you know that is?
Because it's, look, it's between -5 and -6. This number here is greater than that number there. So like if you needed to, you could go, okay, well, you have 5 times 10 to -6.
Right, how is 4?
So is that between
If it's
these?
greater than 1, then it won't be an option, right?
No, it will because -6 is smaller than 10 to the negative.
It's weird with logs. That's why I'm like, I always try to put it between, okay, I know 5.88 is between 5 and 6. So I'm going to go between 5 and 6 on my exponents.
So as long as the exponent is like one of the -5 or -6.
Mhm.
Is that
Yeah, hopefully.
But we don't.
Well, be careful
We
because,
don't care about the beginning numbers.
yeah,
Right.
you're looking at the exponent. You want to focus on the exponent. And Stephanie, if you want just to make some practice, put in your, well, you won't be able to do it on your calculator, but just do a couple of them, kind of get you in that mindset of just getting used to seeing those values. But I always go right between, okay, a pH of 5 gives me that. pH of 6 gives me that. So it's got to be somewhere in between there. Okay. And this is a smaller value, and it's hard to wrap your head around that.
4.55 bigger than 1.
Times 10 to the -6, but it's smaller than 1 times 10 to the -5. So it's in between. So it's in between this range here. Yeah. So if you need to do something like, okay, I know it's 1 times 10 to the -5, 5 times 10 to the -6, and then 1 times 10 to the -6, this is me going smaller. Or do a decimal form. Decimal form might be a little easier for you to see.
Yeah.
And then remember, you got a minute and a half, so
So guess.
no. Guess is the last resort. All right, moving on. Good.
Hey, do you have a needle?
Say again.
Do you have a needle?
No, I do not. We're not popping that thing here. All right. Also, keep in mind, neutralization deals with removing hydrogen ions or hydroxide ions. That's what neutralization deals with. Go. Equivalence point. Make sure you know that equivalence point is similar to a point on neutralization for your titration curve. I also have some more titration curves later on, but make sure that you know what these points represent. Probably one of the more important points is not listed. It's there, and that one is. These are the 2 most important points on your titration curve. Know them well. Yeah.
Can you go over what each of those points are?
Yes. Okay. All right. So here, let me scoot it up.
Do you write this anywhere in here? Should we like write it down?
I didn't write all these points down. I only discussed S and the equivalence point.
Okay.
All right. So Q is the point where all you have is acid for this titration curve. Now, actually, let's do this. Let's go to not that curve, but let's go to these. I think on the next page or 2 pages over. Okay.
What page is that?
It's a page or, yeah, flip it over. There we go. All right. So, first of all, let's identify what does this curve represent? The curve in the middle, what does that represent?
A titration.
Starting with a weak, the blue line, I'm sorry, you may have, it's black and white, I'm sorry. So this would be strong base, and that's your weak base. Okay? And what are we titrating this with?
Strong, weak acid.
Some kind of acid, it's borderline, it's right on 2.
Yeah.
So it's an acid. Let's just leave it at that.
Yeah, it is.
Normally you would be titrating it with a strong. Okay? All right, so the equivalence point is there. So on the equivalence point again is when your moles of acid equal your moles of base. Okay? And the equation that you can use, I know I've said it a few times, MAVA, whatever you want to call it. This is a fast one. MAVA is equal to MBVB.
I don't know how to use that equation.
Molarity, volume. So plug in if you're, say like here it says 0.1 molar of HCl, so there's 1 molar. Your volume that's needed is 50 milliliters. 50. And then it tells us what the concentration, except I cut it out. Let's say that it is, oh, I don't know.
0.2.
0.2. Good. That's a good number. So that'll tell you the volume that you need that you started with, or will use. Yeah, actually. So this will tell you the unknown variable for that one.
only work at the equivalence point though?
Yes, this is only at the equivalence point.
MAVAB, that's only at the.
That's only at the equivalence point. Okay? So that's when moles equal moles. That's what that equation represents for. All right, so Stephanie, back to the points here. So, actually, let's go. So the blue dots that I have here and here, okay? This is where we have only what? Weak base. If we had it above 13, actually if it's above 12, then it's a strong base. Okay? The equivalence point will always, for a weak base, always be below 7. For a strong base reacting with a strong acid, the pH will be 7 if you have equal concentrations of your acid and base and the same volume. What's that? Okay. For a weak acid, or I'm sorry, for a weak base, the equivalence point will always be 7, or below 7. For a strong with a strong, the equivalence point will be 7. When you have the same concentrations, and I can't think of any time that they don't use same concentrations for strong and strong. Okay? The half equivalence point. What would the half equivalence point be for both of these titration curves?
25 milliliters.
And it is a volume, okay, that you focus on. So 25 milliliters is approximately right here. Okay, so be able to scale that down. Then be able to determine the pH. So the half equivalence point tells you when you're halfway there, and it can also tell you the K value for either your base or your acid.
Hold on, what's that red line for?
That red line is indicating the pH. So at the half equivalence point, yes, we have the volume, but more importantly, now we're looking at the pH, so we can do a calculation or a mental calculation to determine what the K value is.
Okay.
Okay, what was that equation for the K when this one was?
For the K, you mean at the half equivalence? Okay, half equivalence is pH is equal to pKa, or I thought I had it somewhere on here, but don't worry about it. The pOH is equal to pKb. Okay. Yeah.
Wait, so how do you find the
You take the negative log. You'd have to have a calculator for this. Unless they gave it to you at like 9. Then you can say, oh, that's 1.0 times 10 to the negative 9 as your K value.
Is that on the
No. I don't think so. No, it is not, because that would fall under the anti-log stuff, which they did not give you. Okay. So you converting pH to a concentration.
No, you're.
Yeah.
You're always asking about buffers.
We would, what we're going to do, we're going to start with a buffer solution, or we'll create a buffer solution as we go along. We won't actually do the titration until we're ready with the buffer. So you're not going to do your titration and then make a buffer. However, the buffering action right here, is that what you're referring to? So it's a buffering region, which means, and this is really important, doesn't mean that we have a buffer. Buffering region simply states, and that's why I put this on here, because that's the only graph or curve that I found with it, is that the pH doesn't change greatly at this point because the acid or the hydrogen is being absorbed by the hydroxide, and it's not changing the pH very much. It's not until we get to the end of this buffering region that the pH goes, because the OH is taken over.
Wait, so why doesn't the pH change a lot in that region?
Because you have, when you add OH, you have hydrogen ions to jump on that and make water.
Okay.
So that's, quote-unquote, buffering region is where we're absorbing all the hydroxide into that solution. Then there's going to be a point where we can't absorb anymore because we're running out of hydrogen or the acid.
I just don't know how to calculate.
Will they ask one of those procedure titration questions like we had earlier?
Could, yeah.
That's frustrating, so I don't know how.
Yeah. All right, let me ask you this because it was brought up and it's not on here. Hang on. Shh. What is the proper procedure for preparing a
Like that,
titration?
Wash it.
It's a burette, number one. Not
Rinse it
like
in water,
that.
and then you put the.
Yeah, hold on.
and roll it around in there.
Hold on. Shh. So you have your burette.
Yeah,
You put some distilled water in it first.
Wash it.
Run it through.
open
Then
the
acid.
cap.
If you are titrating with a strong base, we'll put some of the strong base in there,
Coat it.
run it through. Yeah, so we're coating it.
Put it into the beaker.
Then we will fill it up, run some of it out, get rid of all that before, now we're ready.
Yes.
Okay?
Stop
So you
that.
clean it, you rinse it, then you coat it, and then you get all that out, then you add it. Okay? I'd be upset if you didn't get a 6.
I told Mr. Greg I don't want to get a 5 just because I don't want to go to Chipotle. Or just because I don't want to go to
I said, don't worry, it's not happening. All right. So everybody good with the points actually getting back here? Okay. So getting back to this one, Q, that's when you only have the weak acid or weak base or the acid or base. So the only thing you start with. We haven't started the titration yet. This is weak because why? It's above 2. It's above 2. The R and the T on this actually would represent the buffering region. They would not, hopefully, ask a question about that. R and T.
They're turning points.
What is significant about S?
Half equivalent. pH equals
Okay.
pKa.
What can we say? Okay, good, you got it. What can we say about the HA in terms of A minus?
It's double.
It's the same.
It is the same. Did everybody hear that?
Why?
At S.
At S. At the half equivalence point, and everybody listen, the weak acid is equal to the anions that have been used. And think about it. You're halfway there. You started off, let's say we start off with 1 molar solution in the beaker, and we're halfway there, so we've used up half of it. So that means half of it's still the acid, the other half has lost its hydrogen.
So what the weak acid be at 0.2?
The weak acid, what do you mean, 0.2? No, this is only for the base, added.
But you know how like when they give you that chart on the mock exam, it said like spine point. I don't remember what.
Yeah, and here,
HA.
here's what you're asking. So we started off with, let's say that we start off with 25 milliliters of your weak acid. Okay, everybody listen to this. This is a really good question. Start off with 25 milliliters of the weak acid. Will that volume of weak acid change? More importantly, will the number of moles of that weak acid change?
No.
No. In other words, we started with that. We're actually going to, the only thing we're going to change is from this to that. We're going to rip the hydrogen off once we add the hydroxide. So the nice thing is about the weak acid, that volume's set. That's why you don't see it on here or here. You only see the pH as it changes. So you're going to start with that. You're going to add more liquid. That's what this volume is here. We're adding more of the base to that liquid. So the overall volume is going to change. But not the amount. Let's say amount. More importantly, the number of moles of the HA.
But not the.
Okay, so for the last point.
Are we talking U?
Yeah.
Okay.
I think there was a question on the mock that was saying like what the concentration was.
Okay. So I think at point U,
Like, what
we
does
have no weak acid left. We have a lot of anions left, and we definitely have a lot of the base. Whatever. Once we get to this point right here, all the base that we add just keeps inflating the pH. So if you're asking about who has a higher concentration, I think that's what you may have been asking or thinking about. Let's give some options here. So HA, A minus, water, OH. Okay. So if we were at point U, which one should be in the highest concentration? The OH. At point Q, which of these should be in the highest concentration?
Okay.
Yeah, that's all we got. Okay. So think in those terms. And I wouldn't ask at S because then it's these two are equal.
So why is that you like a point?
a distractor more than anything else. It's to get kids to go, oh, well, that one's all by itself, so it's got to be important. Boom.
Hey,
Yeah.
Craig, why would it be the OH, not the A negative?
The A negative, because we have a certain amount of it, now we're saturating the
What if they
solution
actually
with
got
OH.
RT? So you're just adding more OH?
Yeah, we're just adding it, and we're going ridiculous on it now.
We going ridiculous.
And also, look at where Q started with above a pH of 2, so that means that we have a concentration that's greater than 1.0 times 10 to the negative 2. Or I'm sorry, less than 1.0 times 10 to the negative 2. And this one's above 12, so that means that we have a concentration that is greater than that value. And again, we're talking small amounts, but this is above 2, that's above 12. This actually would have a higher concentration than that 2 point something. Yeah. I would hope that they wouldn't ask a question like that. That would be mean of them to ask. All right. Salts. Make sure you know how salts behave. And what I put on here was the beginning of what? What are these, the front end of? Strong bases. Very good. Okay. And these are the back end of strong acids. So make sure you know your strong acids and strong bases primarily for salts. So if you have something that starts with lithium and doesn't end, or actually, if it starts with one of these metals and does not end with one of these, that's nice. Because you only have to know essentially these 6. Now I also didn't put sulfuric acid in here because it has 2 hydrogens and they won't ask that. But if it starts with this and some other anion, it's going to make the solution basic.
So that's a salt.
This would be a salt. So lithium with something else. And it's asking about pH. That should be another heads up. Okay. If it ends, or the back end of this, and it's not one of those, then the solution is going to become more acidic. What if you have, say, one of those with one of those?
Strong.
Strong salt, right? All the salts are strong that we're going to use for this. But what will the pH be? 7.
Same.
Okay? So strong, conjugates of strong do nothing. Okay? Conjugates of strong, in other words, a conjugate of a strong base with the conjugate of a strong acid dissociates, doesn't change the pH. Okay? So make sure you refresh your memory on that. What if I told you that, no, we could do that. Here, let's do this. Okay? All right, so here's a salt, NH4Cl. You place that in water. We know it's going to dissociate completely, solubility rules. So will that make the solution more acidic or more basic?
Acidic.
If it ends with one of these, it makes it more acidic. Here's how this happens. Again, this will break apart. Make that. We don't care about that. But then the NH4 will break apart and form our most famous ammonia. And ammonia treats everything like a base. And hydrogen. That's why it becomes more acidic.
Ammonia is a base.
Ammonia is a base. It's a weak base. Every good chemistry student should know ammonia is a weak base.
What's ammonium?
Ammonium is right there, NH4.
What is it though?
Well, it acts like an acid. Okay, so it sounds like a lot of you need to refresh your memories on salt. All right. Conjugate acid and bases. Make sure you know conjugate acid-base pairs. How are you going to recognize it as a conjugate acid-base pair?
H, or loss of H.
Has 1 hydrogen difference, and the charge is changed by either +1 or -1, because we added that +1 hydrogen from over here to over there. So that one becomes more negative, that one becomes more positive, or vice versa. So make sure, and I've been helping a few of you out in the mornings, I draw the arrows just to show where that hydrogen went. So you have OH here, there's where that hydrogen came from. Just, I know it's dumb, but it does help a little bit. Okay. What's that?
We were talking about how the meeting wasn't drawn in, so we said she was gonna get us this time.
Okay. So also, don't freak out on if they put, yeah, I'm not gonna say that. Never mind. That's All right, good buffers. What does a good buffer contain?
Nobody knows.
Weak acid and carbonate.
Yeah. It does not contain any strongs. No strongs in a good buffer. All right. So when you look, and I was surprised that they didn't ask a question on the multiple choice, but Monday, you'll see it. They'll give you an option for what would make a good buffer. If you see a strong, make sure you know your strong acids and strong bases. If you see it, cross it off because it won't be a good buffer. Okay. So good buffers are able to absorb either hydrogen or hydroxide. Okay. Good buffer can absorb both hydrogen or hydroxide as long as you have enough or a high enough concentration. Okay. And then there's conjugate acid-base pairs. Just some examples there. Not all of them. Not even close. What does amphoteric mean?
It can exist as water.
In other words, it has to be able to accept a hydrogen. It also has to be able to lose a hydrogen. So if you have something like SO4 with a -2 charge, is that a good amphoteric substance? No, because there's no hydrogen to give away. But it could accept it. Let's say that we had HSO4 with a -1 charge. Is that a good amphoteric substance? Yes, because we can get rid of it. We can also put another one on.
It's the best one that they
Not
have.
the best one.
What is this?
There is no best. It's like I love all my children the same. Actually, I do love my oneness. Yeah, water, and that's a good point. Most of the amphoteric substances, most, but not all, have a charge. Okay? Water is one of the weird ones that doesn't. Okay? It doesn't have a charge, but we can stick another hydrogen on that.
They make it plus.
And make it H3O plus. And don't try to write it as HOH, hydronium.
Yeah.
Don't worry about it. It's H3O plus.
Hydronium.
Very good, Sam. All right, what page are we on? 3?
Yeah.
Oh, that all talk. Oh my goodness, we're almost done.
No, we're not. Craig, we still have.
Well, I meant the period.
School.
Oh, I know. All right, kinetics. Pray to the chemistry gods that this is one of the big questions, not one of the small questions.
Chemistry
Yes,
gods.
I
Okay.
like this.
Chemistry gods do exist if you
What's
pray
the
to
name?
them. Matthew.
Matt.
All right. One thing that I noticed, not necessarily on the mock exam, because I can't remember if they asked it on the mock exam, if you're looking to solve for K, the equilibrium, I'm not sorry, not the equilibrium constant, the reaction constant, and all you have is your rate law. In other words, you have this. Okay, so let's just say it's a first order reactant with a first order reactant. Okay, so let's say that you're trying to find K, and all you have is, we started off with, say, 100%, and then it goes down to, oh, I don't know, 25%. Okay? Would you try to find K by using this equation here? No, you can't. You have to use the integrated rate law equation.
Top ones for first.
First one is top. Notice I didn't put in there the T1 half equation. I hate that equation because this is 0.5, this is 1. What is the natural log of 1? 0. So really this equation should look like this.
0.5.
Okay? So that's a better half reaction equation. Don't use that T1 half because you have to find your K value before you can plug that in. And we try to do some weird things with that. Yes. Yep.
Wait, what?
And if you didn't, then you'd have negative divided by, or I'm sorry, you'd have negatives and they would cancel.
Okay.
Yeah. Yes.
Okay, so that one right there is the natural log of A minus 1.
And again, I'm assuming we start off with 100%. Okay. So if you start off with, say, a 3 molar solution, and there's nothing wrong with doing this. Say if you start off 3 molar and then you're down to 0.25, find out what that percent is. Because, or just plug those in and it'll still give you your value if you know what the time
Those
is.
right there in the box. We don't have one. I like this.
Does parent-
Yes, you have these on your equation sheet. You have these.
Okay, well, can you go over half-life then? And the
Yes.
equations that we need to
Is
use
the
for
test
those?
easy?
Yeah,
Yeah,
what do you
pretty
mean,
easy.
which one?
Like really easy?
Because there's a whole thing about,
Right.
I know we went back, like, I looked at the kinetic sense.
Some of them were the ones that we did on
Okay,
the
so
back.
talk to me about half-life. What do you mean?
Okay,
AR.
half-life, there's one where you can find it for first
Yeah,
order, you
AR
can find
day.
it for second second order, and there's two different equations.
Oh, equations, not the graphs.
No, yeah, well, I mean, go over the graph.
Okay, we'll do the graphs here a little bit later. All right, so
You know which ones I'm talking
I
about?
think you're doing this.
Right? If,
Yes.
like,
That's the one I prefer. But this is the same thing as, whoop, I'm an M. This is the same, gosh, all right. These are the same equation. They're the same thing. Those are the same thing. Okay. I like this, but what's even better is I know that's 1, so I don't need to put that 1 in there, so it's just 0.5. Is that the 2 equations? Because I don't think I ever did this. I do not like this equation.
No, Craig, I'm not.
I can't stand this.
Is that half-life equation?
There's another one.
I personally don't like it because it does work for first order, but it makes students think that they don't have to find K. They can just put it in. And you have to know K before you can find the half-life.
What's the second, or Craig?
For a second order?
Yeah, there's another one.
Oh, okay. So then for a second order reaction,
Okay, the one that you just said, that's for.
that was first order. That's half-life for first. And then this one you cannot zap out. Okay? Which is equal to positive KT.
Okay, so this is half-life of the second order?
Yeah. But what's going to make you mad here is that T1 half. And there's a reason why they don't put this one on there. Is that.
Why?
They don't want to give you that. It's too easy. That would be something you put in your calculator, and that's for second order. That one I have no problem.
Are both of those second order?
These are both second order.
What's first order?
I already did first order.
That's the exact same equation.
T1 half equals 0.69.
These are the same equation.
Just find the.
Mm-hmm.
And these are for half-life, right?
Yeah.
No, I've always, okay, I've had a problem with half-life and finding it when you have to look at a graph.
Okay. All right. So looking at graphs,
Wait, oh crap, I did it.
it's on the video. All right.
I'm gonna pray so much.
No, praying isn't going to help you. Don't do that.
What's training help actually?
No, no, no.
I forgot, Craig.
It's like the try.
All right. Here's what we want to do if we're looking for half-lives. Okay? And I think I made the statement on the sheet here. Look at the y-axis. Guys, shh. Guys, quiet down. Please, please. When it gets to, if we start at 1, when have you hit your first half-life?
Don't yet.
0.5. So look along the y. If this is 0.5, move. If this is 0.5, that is your half-life, if I did it right. Move it right there.
Wait, so what's on the x-axis?
Time.
Always first.
Time will always be on down here. So you'll have some amounts over here, and it won't always be nice and clean where it's 1 or 100. Look at the y-axis, get your amount. You look at how much you start with, go to half that amount. Don't go to half the time. They do that a lot. College Board does that a lot.
So go half the amount, not half the time.
Very good. Never go half the time. Okay? Go half the amount along the y-axis. And then find out what your time is. And hopefully it'll be big enough for Keaton to see what that value is.
I'll throw my calculator.
If you get your reaction that looks like this, and it's, what is the, if this is first order, what's my unit over here? Natural log of the concentration times on the bottom. Okay?
Can we write these on these graphs?
That's what I'm going to have you guys do after school.
Okay.
Yeah. Yeah.
Show us the
So for
equation
that
thing.
right there, you don't have to do any calculation. If it says.
Wait, here or here?
If it says the first one.
This one, yes.
1.5 half-life, you can literally just go to.
Boom, boom, whatever that is. No calculation.
Is that on our first mock exam? Okay.
Yeah.
Because then I tried to find like from an equation.
And is it possible, let me ask you a question here, guys. Is it possible for you to find the K value just using that data right there?
Yes.
You better believe it. Because you have your concentration or your amount, and you have your time. The only variable you don't have is K. So if you needed to say that wasn't 1, whatever that value was there, 7.77, then half of 7.77, okay, it's still 0.5, put your time in.
Wait, what is numerical again?
K is your rate law constant. So it's the rate constant.
So what equation do you plug that into?
Okay.
This one.
That's how
If it's first order. If it's second order, then you plug it into this one. Yeah. And we won't do 0 because they won't
So
answer that.
that second equation, 1 over concentration.
It's second order.
Yeah, but what do you put in? What do you plug in?
Okay? This is 0.5 or half, whatever it is. This is what you started with. Then your time is whatever that is. The only thing you don't have is your K value.
You can only determine it from the half-life.
It's the best way.
Okay.
Yeah. Or if you have a nice clean, well, I'll save that for this afternoon. All right, so I'm going to stop right here, and we'll pick up with more kinetics after school. Kinetics, what were we getting ready to talk about? The charts?
Finish talking about
Just talking charts.
Yes.
You said-
Okay, let's go with the charts here, and I left them blank for you to label. So you already did? All right, so, and I mean, there's 2 options that this could be since there are no units on there. And be sure that you know these straight lines. Make sure you know the negative slopes for 2 of these and the positive slope, and refer to it as that. Don't say that these are downward curves, because curves do that.
Negative slope, and you have to say versus time.
It's nice to say that it's, yeah, make sure that you're always talking about it.
Versus time. So I got a
Well,
formula.
it's whatever's along the y-axis versus time. Yes.
Okay.
So it's a negative slope of, what do you want? Do you want to make this a 0 order just to keep it in order?
Yes.
Okay, so that's 0. So what is the y unit there?
Concentration.
Concentration. So it's just good old concentration versus time. Okay, will yield a negative slope. So if you see a graph like that, because again, with the 0 order, it doesn't change, that rate does not change if concentration changes. That's indicative of a 0 order reactant. So we'll say that this is first order. So what are the units there? Natural log, and make sure that you actually indicate natural log versus time, and again, you'll get a negative slope. Now, what's nice, we were talking about it during 5th period, is that we had the graphs, and I'm going to zip back to an open space here. If you have 2 graphs, say you had this one, and then you had the straight line, and this one was concentration versus time, and this is natural log of concentration versus time, you can find K by using either of those. All right, but if you use this one, don't do this where you have the equation of natural log of the concentration. Whatever that value is, that value there, that's what this is. So don't try to take the natural log of the concentration. I don't know what that'll give you. Yeah, don't do it. So in other words, that is the value. And what's going to be nice about those units? What are those units? Are they going to be positive or negative if we have this plotted out? Very wrong. It's going to be negative. So it'll be negative values here. So again, once you take the natural log of a positive value, it's going to give you negative. So that's good. And that's what we want. All right. So you can you find K doing this? Yeah, we actually talked about it last hour. So find where the halfway point is and then go down in time. So now you have the 0.5, plug that in the natural log of the concentration, then your T.
Is there another way to find out K though, besides the graph thing?
If you're given just a graph and it asks you to find K, I'm going to tell you no. So they're going to base it on what you think is half-life. And so if you start off with 100%.
I'm just confused with the whole natural log thing that you just said, so that's why I'm asking.
Oh, Yeah, so normally they would give you two graphs. So they'll give you one curvy and one that's straight. This is probably the easier one to use.
I thought you wanna use
The
the
one that's
straight.
curved you should use?
I would use this one. If I had a choice, I would use this one. This one's easier for me. Because again, I just go natural log, and this is concentration, right? This is a curve. That's not a slope, right? So then you just take natural log of 0.5, and then I know my time because I can find it, put my time in there, and that, actually take the negative, it gives me my K. Okay, so that's the beauty of the curve. And what's hopefully nice is that it'll give you a little bigger scale that we can see what those values are. Or maybe it falls right on a major line, hopefully. Not like that one problem we worked
So
out.
negative
where-
time, like you make it negative.
I would make it negative, or else if you left this as a positive sign, leave it as a positive sign, then what's going to happen is that'll give you the negative K. This number will be negative, so negatives just wash.
So you just go from the half-life to find what you go from the half.
Yes, so make sure you know where halfway is. And again, we're looking at the y-axis, not the x-axis. Because x-axis, and they'll set it up for you. They'll make it nice and pretty, like they did on that one question. It's like, oh yeah, 1600. I can't tell you how many people targeted that 1600. Because they're thinking half-life is a period of time. It is, but more importantly, it's how much has been consumed or used up. All right, so back to the charts.
Wait, didn't you just rearrange that equation?
Yeah.
Did I just rearrange the equation?
That's
Oh yeah.
all you just did, right?
Oh yeah. This is a fancy stuff here.
That's you one, so it's
All right, so
But, Craig,
yeah,
that equation up there that says the natural log of A minus the natural log of A to 0, whatever. If that's 1, don't you have to take into account minus 1,
Okay, you're saying that this is 1.
right? Isn't it?
What's the natural log of 1?
zero.
That's the beautiful thing
I
about
thought
it.
you were saying that the natural log of.
A 0.5 is going to give me a value. Of 1 is 0, so some number minus 0.
Oh, I thought you were saying that it was some number minus 1.
Yeah.
Okay.
And if they do give you actual numbers there, plugging those values in will still give you the same result, except you have to use those values now. So like if it were, say on that graph, it was 233 whatever, and then halfway, whatever that is, put that 233 in there, and then whatever half of that is. Okay, so whatever half of that is.
Oh, so is the 0 mean initial?
The 0 means initial, yep. And then T is at some point in time.
Okay.
So whatever your concentration is at this T or this time. So when we look at this time here, that's our concentration for that time. 0 is at 0 time, more or
Oh,
less. Okay, so that's why it's just initial.
What if your initial is not 1 molar?
Then plug in what that number is.
You can't do it the way it's.
Oh, yeah, you can't do it the way that I said, just drop it. Because then we'd have to have percentages, which we would change to 1. Or again, if you don't like that, take 233, make that 1, whatever half of that is, make it 0.5. This isn't rocket science, we're just trying to find K, not necessarily the half-life,
So-
but in that point, we can find K.
So if it's not 1 molar, you can plug in the 2
The actual values.
The initial, and then half of that for the.
Yeah. Oh yeah, don't make it harder than it needs to be.
And you'll still, I mean, you can do that even, I mean, it's quicker to do with just knocking that out, but you'll still get the same answer.
Yes. Okay, so go back. Looks like I'm a little bigger than I need to be. There we go. All right, so first order we said was natural log, concentration versus time. And then second order is the inverse of the concentration versus time. Make sure you know those. Okay. Just all you have to know is three graphs for kinetics to determine which one is the rate. And if they give you a bunch of curves, ignore the curves, look for the straight.
And when it says determine what the order is from the graphs, you can just say that it yields a positive, so with inverse concentration versus time, so that's all you have to say.
That's it, yeah. That graph with a positive slope where it's it's an inverse of concentration versus time represents a second order reactant. So just throw in that fancy represents quote in there. Okay. Let's see. Yeah, I put on here, don't use a curve to determine the order, because again, the curve alone, it's difficult to tell, okay? Because if I had two curves, those could both represent first or second order, all right? So that's all I'm saying, is be careful with that, especially if they give you curves and then they give you the slopes. Look at the slope.
They will give you a straight line one though.
Or they will tell you that it's a first order. They'll give you enough information to be able to do that. All right, what I didn't put on here, again, the units. Shoot, I can't believe I didn't do that. Just not thought about that. What are the units for K? And it's specific for the order.
Overall rate minus 1 concentration seconds.
Okay, so it's going to be 1 minus, and then you're going to have time. So it's, what'd you say it was?
1 minus the overall.
So the molarity, so it'll be 1 minus the overall order. Order. What does it say, order there? Now, what I haven't talked about, what is the order of the overall reaction? And this would be a stupid question, but I wouldn't put College Board past it. What if the overall order is 0?
It's the same as
It's
What
just
is it?
1 over time.
It's concentration over seconds.
It's actually molarity over time. That's for a 0 order. That's why I say it's dumb that they would do that. And think about it, molarity over time. Doesn't that say that, molarity over time? Yeah. This would be the unit for K. So the rate is actually equal to K. Because again, when you look at the rate law for a 0 order reactant, I hope you wouldn't write that, but goodbye. Okay, so for 0 order, rate is K. You have your straight line, bam. So that might be a concept. Might be a concept. And
We can just figure that out though too by writing it out, right? And count.
what do you mean writing it out?
If it gives you stuff, then you can like write them.
Explain to me what you're saying.
Like,
How would you do this?
are you saying? Well, I guess we're not giving any value, so we can't.
Let's say that you are given a value. Let's say the rate is 3.0 moles per minute. In other words, that's how much is consumed on that straight line that's given to you. What would your value for K be?
This is for 0 order.
Yeah, for a 0 order.
That.
It's that. Very good. There is no calculation. Because remember, rate is equal to K for a 0 order reactant.
Never
So
mind.
there is no calculation.
That's not what I meant. But
Okay. But it's a good question. And sometimes, and again, this test is all about eliminating the dumb mistakes. I have a name for it, but I'm not going to put it on the video. All right. So don't mistake. So just throwing this out here. What if we had a third order reaction? What would the units be?
1 over molarity squared times second.
Good. Or time, whatever the time is. So don't automatically fall into the seconds.
Yeah, I know,
So,
I did that.
yeah.
I like converted minutes to seconds.
And don't do that. Yeah.
It took
Don't-
forever.
Okay. Anything else that I didn't put on here for kinetics that you're thinking about? Reaction mechanisms, I didn't give any examples for the reaction mechanisms, but again, using the statement, I thought I typed it. Oh boy. Yeah, here it is. To determine the rate law, include all the reactants up to and including the slow step minus any intermediates. That's a great explanation for determining the order based on the steps of a mechanism. Everybody know what reaction mechanisms are?
Yeah.
Like you have A plus B that forms C, and then C reacts with B to form D, and then D plus more C forms E. And then I say, okay, that's the slow step. These guys are fast. Okay, all the steps are going to be fast except for one. So based on this, you can determine the order, right?
Yes.
So we would go right here, eliminate your intermediates. So what would your rate law be?
Rate equals K, A, T squared.
Rate is equal to K, A to the first or second? First, and B
Squared.
to the second. There you go. You got it. No products ever appear in the rate law. No intermediates. Okay? So make sure you identify who your intermediates are before you go crazy on writing out your rate law. Yeah.
Like on those when it like how do you identify? Like how do you tell if it's a catalyst? Wasn't it like a
Okay.
specific product and it goes?
Is there a catalyst in this reaction? Good question.
Isn't it like something that starts as a product and it
Starts
ends
off
as
as
a
a reactant.
The other way starts as a reactant. So if I had,
Oh, okay. Well, then,
say I got
oh, that's
A back over here, okay?
Then that would be a catalyst.
That would be your catalyst. So it's something you start with and you get it back at the end. Okay. Now, is it possible for A to form something over here? Maybe we're forming some Ca and Ca. Is that legal? And then we get it back at the end?
Yeah.
Oh, yeah. That's generally what a catalyst will do. It'll actually involve itself in the reaction, break apart, and then come back.
What's the one that starts as a product and then you?
That's intermediate.
That's intermediate. So here we form it, then we use it.
Okay, and the catalyst, what is it?
Yeah, what's it do? Speeds up the rate of reaction, helps to, it speeds it up by two ways. Lowering the energy needed for the activation energy to occur.
Actually, Greg,
Yeah.
the catalyst wouldn't be in the fast step, it would be the slow step. It can't be in the fast step after the slow step. 'Cause then
Not
it'd be
necessarily. All a catalyst does is help speed up the rate of reaction. Doesn't necessarily mean it's the fastest. So maybe without the catalyst, it might take an hour. With the catalyst, now it only takes 10 minutes. Okay. Where the other steps are like, once they come together, yeah. Okay, so it depends on where it's at in the rate. So it's just like when I go to the grocery store, I walk in, I know what I want. Okay. And then I go and pick up the item that I need. Then I get to the checkout and wait and wait. Doesn't matter how fast I go to get the bread until I get through that checkout aisle. I'm not going to be done with the reaction. So even though a catalyst starts off early and we get it early, doesn't necessarily mean that that's going to be the fast step. Sometimes it is,
Oh, that's good.
but it won't. But it won't actually be the fastest. Doesn't have to be the fastest. Okay, but that's a good thing to consider. What was I going to say? Shoot, somebody asked something. Dang it.
What a catalyst does.
Oh, there we go. Thank you. So here we go.
Lowers the activation.
So it lowers the activation energy. Okay, so if we start off here, what are these?
Products.
Reactants. Very good.
That's what I meant that.
These are the products.
I said-
So if I were to ask you, okay, that line right there is important. That line right there is important. Okay, make sure you know what each of those segments represent.
The activation is the first one.
Can I what?
Let's go over this whole chart right there.
Okay. This is a potential energy diagram where you have your energy here, and this is just like time, I guess. They don't really come out and say it's time, it's the reaction process is what I see a lot.
Yeah.
Okay? So you start off with your reactants, you finish with your products. Okay? And I'm going to show you another one that's you're not going to like. Okay? Oh, hold on, forgot. Let me erase that.
I wrote in a pen.
Wow, that was really good.
There we go. Back page. Okay? So in the back page, sorry. All right, so here's the graph, similar to what I was looking for, except the one that I had drawn looked like, oh, they can't see green, that's bad. Okay, the one that I had drawn looked like this. So we'll use that one for now, okay? So we have this line here, and that one's already drawn out for you there, okay? So this line right here, what is that, or that segment, what does that represent? What is that, right here?
Delta H.
Delta H, good. So it's the products minus reactants. And this is representative of what kind of reaction?
Isothermic.
That would be endothermic. In other words, we finish with more products. So again, don't forget, delta H is the sum of the products minus the sum of the reactants. So your value's higher here than here. which is the opposite for bond energy. Okay, keep those in check. Bond energy is not given to you. So this is a delta H value, and this represents the red line, Sam, sorry, the red line, not the graph that you're looking at.
Oh, see.
The red line represents an endothermic. The one that was originally there represents exo.
Yeah, that's how.
Sorry about that. Didn't mean to mess you up there. Okay. This is the activation energy. What does a catalyst do?
Lower the activation.
Lowers it. Okay. So the activation energy is where you start reactant-wise to where we form the activated complex, the transition things. I think they're calling it transition state. So the intermediates can also be considered that period of time right there. So it's not necessarily reactant, not necessarily product. It's that in the middle part. Okay. Catalyst helps to lower that so we can speed up that reaction. Does delta H change when a catalyst is introduced? No, it does not. Keep that in mind.
Would you say delta H doesn't change?
Does not change when the catalyst is introduced.
You still have the same amount of products and reactants.
Yeah, we still have the same start and finish, okay? But a catalyst doesn't change delta H. It only changes the activation energy. All right, so that's a fun graph.
Yes, that was fun. I like that.
The funner graph is right here below it. Okay? And actually, let me kind of do this. Okay? I'm going to draw a third line here.
What?
A third line on that graph. Of those three lines, which of those represents the particles? And assuming that the area under each of these curves is the same, it probably isn't because I just drew that blue line freehand. Assume that the area under each of those curves is the same. Which of these is at a higher temperature? And before you answer that, this represents the activation energy. This peak up here represents the activation energy. Okay?
Blue.
Blue is at a higher temperature,
Yeah.
but it's lower.
Mm-mm.
But they're moving faster.
Very good. So we have enough particles, or we have more particles. Let's go black here. We have more particles over here that have enough energy that have reached the top of that apex. And so they're now forming products. This lower curve represents more particles at a higher temperature. This graph you will see Monday.
Okay.
Something like this on Monday. If not one time, maybe two. They might ask you multiple questions. Okay? So what you want to look at is this right here. That represents the number of particles. So always look along your y-axis. So you have your number of particles. We have more particles right here for this first hump that haven't got enough energy to reach the activation energy or to form the products or form the activated complex, which then would form the products. Okay? So don't think, oh, it's a lower hump, therefore it's lower temperature. We have more particles that are actually able to form the activated complex. Okay? All right, so go back. Everybody good with those two graphs?
Yes.
We'll come back to these in a little bit. And we're not going to get done in 2 hours.
Wow.
All right. Anything else with kinetics? Make sure you can use table logic. Look at the table, the data given. Be able to determine first order, second order, zero order. Okay? I don't have an example. You have tons of examples. Let's make sure that doesn't reboot. 4 hours. Okay. All right. Any other questions with kinetics? You're going to see it. I promise. You'll see kinetics. Yeah.
On doing those table things when you're looking at them, I know you don't have one up there, but
Okay.
when you are looking to see if it's doubled or tripled, since they always use like something times 10 to the negative whatever,
Okay.
how are you actually telling if it's like double? Because sometimes is it always going to be exactly doubled or exactly?
I would say, here's one.
Yeah.
Okay. I would say I haven't seen a whole lot where it's not. I've seen it
Okay,
one
so-
year. The one time I gave you that example in the homework packet where you'll always be able to to find a likes for at least
Okay,
one
so
of them.
meaning that experiment 1 and 2
Mhm.
are,
The same for NO,
so does this mean you're finding the order for that?
I'm finding it for oxygen.
Okay.
As this remains the same, I want to know what's happening here. That's 3 times, that's 3 times. And you'd use your calculator. I can't look at that and see that,
Is
it's
that
3 times.
first?
So, right, that would be
Wait, so do
representative.
you type in your calculator 8.52 times 10 to the 3?
I would go the bigger number over the smaller one, that'll give me the whole number. Or else you'll get 0.3 repeating.
Wait,
So you divide 2.56 times 10 to the first divided by that?
Yeah, or 0.256 divided by 0.08. Yeah, what you said.
So like using table logic, so even if you, so you can just divide the numbers or whatever, and then you can just say, as this doubles, that doubles, so it's first order.
That is perfect. Did everybody hear what she
Yes.
said? So that's all you have to do to justify. If it says justify,
That's
just
so much faster.
somewhere,
Yeah.
give details, yeah, so,
So if it's second order, then as that triples, the other thing's gonna,
It's exponential.
gonna
Yeah,
go 9
9
times.
times.
bigger?
Yeah.
yep. So it's just like doing whatever the value is, square it, so it's exponential.
And 0,
0 is, the values are the same. So as you double it, these would be the same numbers.
okay.
Yeah, so as you double one, it remains the same, or triple it, or quadruple it, it
Wait,
stays the
I
did
same.
know
you just
for
say the initial rate triples or whatever?
That would be
As the
for,
concentration triples, the.
that's first order.
The rate triples also, so it'd be first order.
That's first order,
So
Well, I was talking about the estimation.
sorry.
So for like first
Yes.
and second, that the rates are independent, and then for 0, they're dependent because they're exact, they're the same.
Good. But you don't have to go into that much detail. You can just say, as the concentration changes, the rate didn't. That's a 0 order reactant. Yeah, keep it simple.
Yeah.
Does that make sense, Stephanie?
Yeah, so when you're saying, if it's second order, you would say like, okay, the concentration tripled,
I think we have one. I think this is triple.
okay, so when you say it triples, then how do you express like the rate? You don't say like 9 or like.
Yeah, you do. Say it's 9 times faster.
Oh, okay.
Yeah, if I tripled the concentration or I 3x the concentration,
Uh-huh.
the rate is 9 times faster or 9x faster. That's perfect. That explains it totally. Back to the action. All right, so kinetics good?
Yeah.
Yes.
Nice, good. All right, thermo. Make sure you know thermo like the back of your hand. You're going to see so many questions about thermo, it's not even going to be funny. Okay? Probably the one thing that I want to emphasize the most with thermo is make sure you know which delta G it is that you're using. All right? If you have voltage, don't even think about using these two. All right? If you have delta S values, there's one to use. If you have an equilibrium situation, use this one. Make sure the R that you're using is not the gas R. Which one should you use?
The 8.13.
Very good. That's the only one that has joules on it. What's the most common unit for delta G and delta H? Kilojoules per mole. What's the common unit for delta S?
Joules per mole.
Joules per mole. All right, so we'd have to, if you were asked to do a calculation, and the table would give those units, so make sure you're looking at the units, but delta S would be in joules, make sure you convert that to kilojoules, because you're going to be using this equation most likely. Open up for me, come on now. You'll be using that calculation, and we have to subtract the like units, so we can't just say, oh yeah, I'm feeling good about that one. Yeah, how many joules are in 1 kilojoule? 1,000, very good.
That's gonna be over test.
I did that one.
1,000 joules in 1 kilojoule. Remember, kilo, joule, 1,000 joule, that's what that means.
What a great Maggie King. We can go all the way
Kilo,
back to
joule,
Maggie.
1,000 joule. Okay? Doesn't mean kilos 1,000, 10 to the 3. All right. Make sure you know the terminology, thermodynamically favored, not thermodynamically favored. I'm going to admit I still use spontaneous and non-spontaneous. How many times did they use spontaneous on the second mock? None. So get used to this. All right. So no thermodynamically favorable.
And it's, wait, is it, I might be thinking of something else, but it's not spontaneous if it has an energy source, right?
That's electrolysis. We'll get to that.
Okay.
Yep, we got those too. Heat of reaction, there's a couple ways that you can determine heat of reaction. You can use the equation that's given, where it's products minus reactants, bond energies. And I put on here, question 27 on your mock exam was a good question that over-illustrated, over-explained, over-asked. But all it is, it boiled down to bond energies, which really stunk. So in other words, it takes energy to break bonds. You lose energy when you make bonds. Remember that. That's what's happening on the reactant side. So when you go from reactants to products, you're breaking bonds, okay? So it absorbs the energy, and then so it's endothermic, and this is exothermic, okay? And how do you know? The equation even says that. Delta H is equal to sum of the reactants minus the sum of the products. Boom, negative, exo.
So, are you saying that reactants are always endo?
For the bond energies, it's going to be endo. Lay it down and get out. Oh, you want your phone back, probably.
I said who's all gonna be here.
Hey,
Go lift, go make yourself strong.
This was this morning, he said who's all gonna be here, and I said it's not Timmy.
Craig, losing energy when you're making bonds.
You are making bonds on the product side.
Hey,
That's
Timmy.
the loss of energy.
What's up, Timmy?
And then you absorb
Bye,
energy.
Timmy.
See you, Timmy.
Stay out of trouble.
Energy, like bonds.
Yes, when you absorb the energy, it breaks bonds.
Mr. Craig.
Yes. In what way?
I don't know, like, I always end up getting them backwards.
Are you talking about position on a balanced equation? Are you talking about what they do?
Like, you know that one time you had us figure out if this is like, if water, you had
Oh, I know what you're doing. Okay, I got you.
those situations where it's like, if like you're on a stove or something.
I got you. I can give you an example here.
Not like you're not on a stove.
Okay.
You could be endothermic.
All right, so we've got our beaker filled with pure water. And I've got my,
And this might help, like, with that question number 27.
Oh, make a splash, Mr. Craig, make a splash.
so we're gonna put that in the water. And it makes a splash. All right, as a result, before we put this in, it was at 20 degrees. Okay, when I put this in, it went into the water and broke apart, and then the final temperature of this was 40 degrees.
Oh.
Okay, so here's my question. The solid, the water. Okay,
See, I would have said that the solid was exo and the water was endo.
and I would say that is correct.
What?
So why is the water,
Wait, hold on.
is the water 40 degrees or is the thing 40 degrees?
The whole thing.
40 degrees.
So as a result of putting that solid in there, that dissociates. In other words, this is,
Yeah.
oops, that's a reaction. Okay. So I'm putting something in that will dissociate in water. Once it gets in there, it breaks those bonds. Okay. So it dissociates. And as a result of that reaction with water, the temperature went from 20 degrees, the water temperature, whoop,
Oh, okay, I thought you meant the temperature of the thing went from 20 to 40.
dang it. All right, so the water went from 20 to 40.
Okay, yeah,
We don't know what the temperature of the solid was.
okay.
Okay, but we can measure the temperature of the water. So if the water went from 20 to 40, then we're going to say that the water absorbed the energy while the solid lost it. Okay. Yeah.
Okay.
Is like the process of dissolving endo or exothermic like in itself?
Depends on the reactant. In other words, you've got cold packs, you've got hot packs. If I take sodium hydroxide and put it in water, it gives off a lot of heat. But if I take ammonium, can't remember what's in there, it depends on the substance. So substances make the water solution cooler. I know, it's not consistent, so.
For example, this one would.
This one?
It's exothermic, because the dissolving
Correct.
is losing.
So as it's placed in water and allowed to dissociate, it breaks
What's
bonds.
this called, like calorimeter?
No, this isn't a calorimeter. Calorimeter is where you take a metal, put it in there. There's no chemical reaction, it's just a transfer of heat. Yeah. That was another question that we went over.
Go over the other part.
Wait, what do you mean?
Sorry about that.
Okay, the other parts of exo, okay, maybe A plus B
Okay,
makes
so Craig,
C and
if
D.
you're on a stove and
Uh-huh. Am I in the pot of water?
Yes.
Okay.
And if the water is boiling, does that mean that the water is endothermic and this pot
Either the flame or the source of heat
is exo?
is exo. So it's losing heat and the water is there to absorb it. And if I'm nearby, I'll absorb it too. In other words, as you walk by the stove and you're like, ooh, that feels warm, you're now exo.
Wait,
No, you're
exo?
endo.
I'm sorry, you're endo. You're endo. It's losing. Thank you. I was thinking going outside. I was doing my next example where you go outside and grab a snowball and it feels cold.
You're exo. 'Cause
You're exo because now the heat is.
Okay, that confuses me.
And then the pot is endo because it's a.
The outside snowball thing confuses
Yeah,
me.
let me find my statement here. Where is it? Here, this one right
You're
here.
giving off the.
Here, look at this statement. Heat moves from areas of high heat to areas of low heat. So when I touch something that's not as hot or have as much energy, it feels cold to me. When I touch a hot plate that has more heat than I have, it feels hot.
Are you endo there?
At this point on the hot plate, I am. Here I'm exo.
Is in, so it's endothermic.
Okay. When I touch something cold, I'm exo. When I touch something hot, I'm endo.
Because like a snowball, like you make it melt, so it's gaining heat because you're making it melt.
Perfect. You got it.
Make bonds next.
Okay.
Craig?
Yeah.
We don't have to go over everything. Can you make sure to go over the whole SP thing that has to do with the Vesper?
Yeah. Yeah.
Energy is absorbed to break.
Yeah. All right. So in this reaction, where's energy at?
Can we just stay in this room till the exam?
What? What'd you say?
This situation, where's heat at?
The product side.
Shh. You agree with her?
Wait, what happened?
Okay.
Yeah. Wow.
Wait, what did you
Heat.
say?
Is it over here or is it over here?
It's on the product.
It's on the product side. It's exothermic. So it loses heat. That's just where we put it for Le Chatelier.
That's how it is.
That's the way it is. Yep.
That did how we did.
And it does go hand in hand nicely with bond energies, but hey. All right. Hess's equation. Make a note, circle that, because we don't have time to really show examples of that. This is something that you will see. I saw it a couple times in the second mock exam, where they're giving you equations that have heats of formation or heat period. Sometimes you might have to flip it, sometimes you might have to multiply it by something. Okay? There's a lot to do with Hess.
Where's that
So,
still?
Hess, it's underneath, it's in thermo, right here. Okay. Also, make sure you know this process. I think we've pretty much beat this to death, at least in here. Okay.
It'll be too weak to show up for the exam.
What's that?
So maybe it'll be too weak to show up for the exam.
This will show up on the exam. I promise. Okay. All right. Anything else thermo related that's kind of important here?
Where would you find the Hess's thing?
Hess, it would be in the thermo section, near the end of the thermo section. So I don't remember the day right offhand. Okay. All right. Electroredox, NERTS. Okay. NERTS. Make sure you put this in your calculator. Okay. Okay. Just so you don't do something dumb, they'll probably ask it on either multiple choice and the free response. But the NERTS equation, you don't have to know how to use the equation. You just have to know the concept. What are standard conditions?
Voltage increases.
No, what are the standard conditions? Yeah.
280.
25 degrees, 1 molar. The most important component of that is the concentration is 1
Is
molar.
that like the same as STP?
No, STP is at 273 Kelvin. This is at 298. But what I'm getting at is all those voltages that are given to you are at standard conditions. What? What's the matter?
Conditions and STP are different.
Yeah, standard temperature and pressure and standard conditions are two different things. Yeah, STP is at 1 atmosphere and 0 degrees Celsius or 273 Kelvin. Yeah.
What is 298? Why do those use that?
This is supposed to be quote unquote room temperature.
Wait, but like 298 Kelvin, that's the same thing as that?
Yeah, that's 298.
Okay.
Sorry.
I use Fahrenheit, man.
No.
Here.
All right.
Mr. Craig, are you a Fahrenheit or a Celsius kind of guy?
I can swing either way. I'm all right.
I can't say
Mr.
it
Craig,
anyway.
Yeah.
what's the Nernst equation?
All right. So the Nernst equation, which you don't have to know,
What is it?
98 is
it is, trying to remember right offhand, the cell minus 0.0593 divided by the number of n, and then natural log of q. I think that's it. There might be another thing, but all we really care about is this. And this. That is very important. Okay? So it's going to tell you whether or not the voltage goes up or down if we're not at standard conditions. If we're at standard conditions, what happens to the back end of this equation? So what we really want to focus on is Q. And that's what I have here. So it's the anode ions over the cathode ions. So when you look at your galvanic cell, okay, how do you know it's a galvanic cell, first of all?
Spontaneous.
2 chambers, very good. So there's 2 chambers,
And it has a salt bridge.
and it has a salt bridge. If I take that salt bridge out, what happens to the reaction?
It's not spontaneous anymore.
It's gonna stop eventually.
Nothing,
Nothing happened.
Good. So the reaction stops, put it back in,
It
starts, take it back out, stops, put it back in.
It happened.
Okay, so that's really important. And you can actually, if you had a voltmeter on there, see that happen, is that you put it in and take it out. All right, so again, I erased it, but the anode is what happens at the anode.
Reduction.
Oxidation,
That's what I meant.
AO, cathode. Keep the vowels together, keep the consonants together. All right. Now, also keep in mind, now listen, this is really important, that these concentrations for these ions, only ions. We don't care about the solids, because again, in an expression, we can only have aqueous and gases. Well, gases aren't going to appear in the Nernst equation. So if we have, say the voltage is increasing, it's because Q is less than 1. What that means is that this is higher. The concentration for the ions in the cathode are higher. If we have a decrease in voltage, then that means that the anode ions are higher. So have this memorized. And you'll have to memorize it. Okay? I would not put this in your calculator. Don't have that stored. That's not going to do you any good. All right, oxidation numbers. Make sure you can determine the charge. Make sure you can determine the charge on any particle. If it's in its natural state and it's all by itself, what is the charge?
0.
Very good. Real quick, galvanic electrolytic or electrolysis. Here are 2 diagrams that actually show what's going on. In a galvanic, this is a thermodynamically favorable situation. In the electrolytic, or the electrolysis reaction, this is a non-thermodynamically favorable situation. Okay? Yeah.
For spontaneous, does that mean G is negative?
Yes.
Mr. Craig,
Okay,
what's
so what's the one that the voltage is positive and spontaneous?
That's all situations. When the voltage is positive, then we have a negative delta G. So if we have, say, an electrolysis reaction where we have a negative voltage, then that means that we have to pump the energy into it, the electrons into this reaction to get it to take place. And do we want the highest negative value or the one closest to 0? Closest to 0. We want it negative for this, but we want it closest
Oh,
to
I
0.
thought you meant the one. Sorry, I'm
Yeah.
thinking of
On
something
this one, the highest positive value.
else. I was thinking of something else.
What's that?
What's the smallest negative?
In other words, which is closest to 0? That or that? Yeah, 0.95. So if you had 2, we're going to flip this guy, or we're going to look at the thing that has the lowest voltage closest to 0, or the highest voltage
So
closest
which
to
one do
0.
you flip?
We wouldn't flip one. It would be...
Ron Delacca, please call extension 5321. Ron Delacca, extension 5321.
There was a question. Was that one of the BS questions?
There was one about.
On the mock, yeah, on the mock exam, it had what would be formed at the cathode. So we had 2 choices. We wouldn't flip any of them. We would look at those 2 values that are negative, that's closest to 0. That's the one we would pick. And it was the hydrogen oxygen,
Wait, close to
not the
0?
lithium. Yeah, negative that's closest to 0 for this reaction. Because then we don't have to supply as many electrons. And so it's always going to actually form the first thing that's possible, the lowest voltage, or actually quote unquote the highest voltage, is going to come out of the solution first.
I looked at it and I saw like which one was the reduction one and which one was oxidation.
Well, they're both reduced.
Well, yeah, but I would saw like which one you would want to flip, and that's.
Well, the lithium one is the one that you would want to flip.
Yeah,
but
that's, yeah, so I got the right answer.
Yeah.
Is that an okay way to do it?
I wouldn't
Because the
flip
redox
any of
is-
them.
Well, I don't know, not flipping.
You would
the
flip
redox.
here, but not here.
Well, like, the redox is because it is closest to 0, right?
Mhm.
Well, the negative number.
Right.
And so the lithium, technically you'd want to flip it, but you're not going to.
Correct.
Mr. Craig,
Yes.
I know for galvanic cell, you want the highest,
Positive voltage.
how about electron?
Electrolysis, we're going to go with the highest negative value. So this is the highest negative value. 3.05 is the lowest.
If you
Right.
wrote the,
So close to 0?
Yeah.
if you wrote the equation for that, then you don't flip either of them when you do it? Or do you?
Depends on the problem, the question. Just know electrolysis is going to be negative. It's going to have a negative voltage. Okay, that's the most important thing. And then on the question that was on the mock exam was asking what was going to be formed at the cathode, and you had 2 choices. Then you pick the one that has the highest voltage,
And then-
closest to 0.
So that's highest voltage.
Yeah.
And then you choose the ions because you don't care. You only care about the ions. You don't care about the solution. Right?
Yep.
That's what I did wrong. I don't because I couldn't remember. I did it wrong.
Okay. Some real quick things. Make sure you look over this, like oxidation reduction, what metals prefer, what non-metals prefer. Make sure you can do an acidic redox reaction. Make sure you can do a basic redox reaction. Here are the steps. Check that out. I even gave an example for a basic redox example on the steps in addition to what you do for acidic redox. Atomic theory. 20% of the AP exam is going to be atomic theory.
Holy heck.
Okay. So it deals with trends. Make sure you can explain trends. Make sure you can deal with everything related to the periodic table. This is easy.
I have no idea about S.
Okay. I haven't seen these equations be used in a while. Doesn't mean it won't happen this year. Make sure that you know how to use the speed of light equations.
Wait, which one? Oh, okay.
Yeah, speed of light's the second one. This is the energy. Realizing that that's a constant. Where are you? There it is. Okay. And also realize that these both have a common variable. So often what could be asked is they'll give you a wavelength and ask you what is the energy of that. You would have to use both of those equations to do
H is
that.
given to you, right?
H is a constant, yeah. So if you're given the wavelength, you would have to find the frequency to then take the frequency and plug it in to solve for the energy.
Got it.
Okay. All right. Make sure you know quantum numbers. Okay, so a set of quantum numbers, and I gave an example down here, the 3, 2, 1. Okay. You should be able to look at a set of quantum numbers and pick on the periodic table where that element could be at. Okay. First energy or first number represents the energy level. The second number represents what?
The sublevel or the.
What do you mean? The orbital, right? So it's an s orbital, p orbital, d orbital, f orbital. So it goes right down the line from 0 to essentially 2. So 0 is a s orbital, 1 is a p, 2 is a d, 3 is an f. Okay. So you can say, okay, it's in the third row. I'm sorry, third energy level, which is in the d orbitals, which actually lies in which row? If I'm looking at d orbitals and I'm in the third energy level, what row on the periodic table am I at? 4. Remember that. Okay.
Wait, say that again?
Okay. Looking at your periodic table, where are the d orbitals at? Third row or fourth row? Fourth row. So this doesn't tell you the row, this tells you the energy level. That's energy level, not row.
Why is it not the same?
Because for D and F, they're different.
They're 1 less.
Yeah, well, D is 1 less, F is 2 less. So that's one reason why you want to slow down, especially on a question like this, where it's going to take you maybe 15 seconds to answer it. Don't take 5 seconds to answer it and miss it. Okay? Spend a little more time and go, oh yeah, third energy level, not third row. This is d orbitals, And then we don't care about the orientation. How many different orientations could we have though for this?
5.
5, good. So it goes 2, 2, 1, 0, -1, and -2. If, let me ask this, say the value was 1 there, how many different orientations can you have? 3, okay? Because again, the 1 represents what? P orbital, and we have 3 orbitals in the P's. If this were a 0, how many orbitals?
1.
Because we can only have 1 orientation for S. Keep the basics in mind. All right, yeah.
What's that 1/2 number at the end?
Say that again.
That 1/2 at the end?
Don't care.
Don't care.
We don't care about the half, the spin. It's either going to be positive or negative, and it's not wrong if it is. Okay.
Okay, this is a really dumb thing to forget,
Okay.
but like, when you're doing the electron configuration, do you go 3p to 3d or 3p to 4s to 3d?
What do you mean?
Like, you know what I mean? It's like 3p on periodic table and 4s to 3d, but you still do 3p to 3d, right?
Okay.
On
So,
that one, like when you're writing it, you'll know.
okay. Are you saying you go 3p
Yeah.
to
When you're-
4s,
Yeah.
okay, and then 3d?
So when you're listing the electron configuration,
Oh, yeah, we talked about that. Is that carbon chain?
Okay. Now, let's say that we're forward there, okay? Is this a good orientation to leave it at? Okay, so we got everything, we've written the complete configuration, and I stopped here at 4s2 because I'm showing chromium. Is that a good one to leave? Why, Stephanie? Why is that not good?
Because of the half-filled
Good.
d orbital.
1, 5. Okay, always ask yourself, can that be half-filled or emptied out to make the D's happy? And only the D's get happy in these 2 rows.
Is that because this went from a higher to a lower?
Exactly.
But then why wasn't the other one also do that?
Because then we wouldn't have a half. So we have half of the orbit, or the orbital's half filled. It's kind of like everybody has their own room. If we take that other one out, now somebody's like, he's got 2, but I still have mine. And the one that has 2 isn't happy until you're forced to share. Okay. All right.
That's a good analogy.
All right. One more.
I don't really got a lot of good.
Coulombic attractions. You don't care about the equation here? Okay.
I remember when he put that up on the board and we all like freaked out. Back in the
All it's talking about is force, and really what we really care about is this guy and this guy. Okay. So what happens is, as the diameter or radius, and you'll see it written a couple of different ways, as the radius gets smaller, what happens to the force?
Stronger.
Goes up. So as that number gets bigger, okay, then this gets smaller. So make sure you know the relationship, mathematically speaking there.
I know that.
So if you're looking at, say, this as an ion versus this as neutral, okay, this has those electrons bound a lot more strongly than this one. We could probably take an electron away very easily.
Yes.
Because it's not held on as tightly to the nucleus. Okay. So Coulombic attractions are going to be nice in helping you to explain a lot of things. Just make sure you have some explanation to go along with it. Make sure that you talk about intermolecular forces or intramolecular forces and the size. You put that in there with saying Coulombic attractions. You don't have to spell it right. So if you write Coulombic, whatever, you don't know how to spell, then...
I thought you just say Zeph.
What's that? Zeph is another component there. Okay. All right. Ionization energy. What's in ionization energy? An electron. Very good. And as we go from left to right, it gets higher. Higher. Ionization. It gets harder to take that electron away. Why? Coulombic attractions. As that gets closer to filling up the orbital, the Zeph increases, so there aren't as many core electrons blocking that negative charge, so it brings it in, makes that radius smaller. Shh. All right, make sure you know the difference between inter and intramolecular. Which one's stronger, inter or intra?
Sure.
Intra. Between atoms is so much stronger than between molecules. And I saw a question a couple years ago, said, okay, we got water. When I boil water on the stove, it turns into hydrogen gas and oxygen gas. Is that statement true?
No.
No. Think about it. Every time you cook, you'd be blowing your house up. All right? But I'm going to tell you, I can't tell you how many students were going, oh yeah, every time, that's what happens. No. The reason why it doesn't do that is because the bonds between the hydrogen and oxygen are really strong. The bonds between the hydrogen, or between the molecules, are weak. That's why we can take water as a liquid into gas. Not hydrogen gas, not oxygen gas.
Blow it up like enough, will it happen?
No, electrolysis. We'd have to use a different technique there. It doesn't take much.
But I can blow up my house.
Don't do it, Sam. Don't do it, Sam. Also, hydrogen bonding. Where does hydrogen bonding take place?
No, hydrogen with no.
Okay. So if we have, say, water.
Mr. Craig, I've had enough of this.
You don't know this thing. You don't know anything. Okay? All right, so hydrogen bonding, where does it take place? Is this a good situation? Is that a good situation? Is that a good situation?
No, the first one.
Okay. So could hydrogen bonding take place between these two hydrogens?
No.
Never. Okay. That would be a dispersion bond or force, which is really weak because as soon as that takes place, what's that water molecule going to do? Going to go away. All right. So let's move you here. Is that a good hydrogen bond?
No.
It's the same thing. What about here?
No.
Yes.
Yes.
Because now we have the negative end of the oxygen to the positive end of the hydrogen. Now we have another one. That's what makes it strong. Okay. So make sure you know where hydrogen bonds take place. That is not a hydrogen bond. Does not take place between atoms.
Wait, what?
That is not a hydrogen bond. No. That's what kind of bond is that between hydrogen and oxygen?
Intramolecular.
What kind? Give me a name.
Polar covalent.
It is polar covalent.
Is that
Very good. Polar covalent means that these electrons are being shared unequally. Yes, sir.
Okay, so back to the
Wait, was that right?
radius
It
part.
is right.
There was a question on a mock exam that was saying, we were talking about
I don't get
the
it.
largest to smallest radius,
Mhm.
but it had one that were, pretty sure
Boys,
it
boys.
was
It's picking all that up.
SCO, AR, K, and CA.
Okay. As neutral or as ions? Hopefully ions.
Probably.
Okay. So you want to look for the, here's what you want. You want the nucleus that has the most protons if we have the same number of electrons. That's going to give you a small radius. Okay.
No, it was on
So
here and I got it.
what I didn't put on here was isoelectronic. What's isoelectronic? Same electron configuration or same number of electrons. So if you have, say, 20 electrons, but you have an element that has 25 protons versus an element that has 17, protons, which radius is going to be smaller? The one with 17 or the one with 25? Greater nuclear attraction. Okay, Coulombic attractions, we have a greater force. It's going to draw those in. Okay? So the higher the positive charge in your nucleus versus your negative charge will make this radius small. This one will be larger. Think about it, common sense. We look at the nonmetals. Chlorine, what's the common charge for chlorine? -1. Why? It gained one more electron than it has protons. Okay? So it gets bigger when that happens. Okay? So don't forget, the basics when answering questions like that. Shh, please. All right. Make sure you know dipole-dipole, London dispersion, and ionic, which deals with VSEPR. So you have to be able to draw the VSEPR shapes. Because if it's not a polar compound, or if it is a polar compound, what are your options for intermolecular? It's a polar. It's either hydrogen bonding or dipole-dipole. And then you go the next step if it has a hydrogen bound to a nitrogen, oxygen, or fluorine. Okay? All right. So the intramolecular forces, here we have our covalent bonds. And if they're sharing those, and covalent means sharing. So if it's unequal sharing, then that's a polar covalent bond. And if it's unequal sharing, I'm sorry, if it's equal sharing, then it's non-polar covalent. Unequal sharing is polar covalent. Okay. And ionic bonds are between metal ions and non-metal ions. Make sure you can interpret the PES data. Boys, guys, if you want to go out in the hall and talk, that's fine. Please. Okay. So looking at the PES data, make sure that you can read the scales, okay, the lines. Sometimes they'll represent how many electrons are actually in that orbital. Sometimes it might be 2, sometimes it might be 3. Just look at the relative heights, realize that you're going to have S's first, then P's, and then start over a new energy level. All right. Also, I'm trying to remember that they have the nucleus here. The energy goes up this way, so it's backward for, or is it the other way? No, it's that. Is it that way?
Yeah.
Okay. So the energy gets higher. But whatever, look at the values. Please look at the values. Okay. I don't think the PES questions are going to be extreme because they're new.
Higher the other way, that's great.
What's that?
Isn't it higher the other way? Because the nucleus
Yeah.
is stronger?
Yes, yes, you're right. So it's harder to pull the electrons away from those that are closest to the nucleus. Yeah, I knew that didn't look right because that looks normal to everything that we do.
Yeah.
Yeah, it was the opposite way. Thank you. All right. Reaction solubility rules. Make sure you know how to write a net equation. Not necessarily a net ionic equation. That's also good. But a net equation only involves those things that change. So the one question that was on the mock exam asking you to write the precipitate reaction. Yeah, true, you have a lot of things going on, but only that which forms a precipitate should be in the net. That which forms water should only be in the net. Okay, so make sure you know what you're forming. That's the only thing that goes in there. Conditions that involve change, changing state. In other words, going from aqueous to a solid. That actually constitutes a change. Gaining or losing electrons, so the charges change. Switching partners. Even though the charges may remain the same, they're switching partners, forming something else. And that one would be hard to detect without being told so, but the color change. I have on here, be sure you read and look at the given balanced equation for the states and the coefficients. I can't tell you how many times, especially when you're designing an ice chart, how people just conveniently leave out those values. Okay? They're not all ones. They're not all twos. Make sure you look at the coefficients, especially when you're doing ice charts. Slow down.
Is that a multiplier on X then?
It is. Yep. It is. All right, Vesper. Fill out that chart.
Done.
Oh, it's easy.
Okay, tell me. What's this one?
Trigonoplanar.
Trigonal planar. Good.
Okay. Oh, next one. Okay. Tetrahedral. Trigonal bipyramidal. Octahedral.
Okay, so hold on. Below the tetrahedral is what?
Oh, trigonal pyramidal.
Trigonal pyramidal. So it forms a triangular-based pyramid. So trig pyramid. Okay.
Trigonal bipyramidal.
Trigonal bipyramidal. So it forms another trigonal-based pyramid, but we have two of them. So the bipyramidal.
T-shaped polymer.
And so seesaw, take one away, actually forms that nice little seesaw that we played with. And this is what again? T-shape, good.
Octahedral.
Octahedral and square pyramid, good. Okay, know that chart. Also, if you are asked to identify, it's rare that they ask over here, but I'm not going to say that they're not, but generally it's over here. Okay. So make sure you know the angles, make sure you know the hybridization, make sure you know formal charges, make sure you know how to draw out correct Lewis structures. Does everybody have that? Because I can't, it won't stay. What's that?
Like the SP in relation to the stuff.
Okay. The way that I remember it is how many things are around your central atom. So if I look at the linear, I have two things. Okay. So I have two things, two letters. Trigonal planar, I have one thing with three. I have three things. Could be elements, could be lone pairs. Okay.
What is it like me and those? Like, are they just
The hybridization actually has more significance with the type of bonds that it has, like sigma, pi bonds, things like that. The total number. So if we were to form that. You don't need to know exactly what that is yet. Okay. So the number of external things, that's how many letters you should have.
The highest is SP3, wait, SP2?
D2 SP3, which is 5.
If you just have,
Oh yeah, you're right, 6, thank you.
if you have two atoms bonded, what's their hybridization?
Linear.
So it's-
The hybridization, they wouldn't ask that, but
Okay.
it's a linear shape because there's only one thing. Actually, it'd just be a sigma bond,
Okay.
unless there was a double bond.
Yeah, where's
Yeah, don't worry about that.
Sigma is single.
What's that?
Pi is 2. There's always one sigma in pi.
So here, below. Are you asking about what it is?
Yeah.
Okay, so if you have, let's say,
That's 2.
2 atoms. Sigma bond is a direct connection. Pi bond up here and here, if that's a triple. So what happens is there's bonding, there's sharing of electrons are taking place in those p orbitals. Here, this is a direct connection through the s, yeah. And these are 2 p's that are able to
Wait,
share
so that
electrons.
triple bond would be, that's,
Sigma is in the middle, pi pi. And you don't need to know that. All you need to know is, actually, you don't need to know this drawing, what I just did.
well, yeah.
This is organic. We'll talk about that next year, or 2 years.
If we do
Also, formal charges, make sure you know that group 5A likes triple bonds or a total of 3 bonds with 1 lone pair. Group 6A likes double bonds, and these are all external atoms. So double bonds or 2 bonds with 2 lone pairs. And then group 7 likes a single bond with 3 lone pairs. Okay? That is a quick way to draw Lewis structures. Carbon always goes in the middle. How many bonds does carbon always have? 4. Hydrogen is always outside. It only can have 1.
Correct.
Yeah.
What's the one that has 6 instead of 8 electrons?
Boron.
Boron's the moron.
Boron's the moron.
Yeah. Yeah. Also, remember CNOF. What's special about CNOF?
They can have,
Can only have an octet. Good. So, must have an octet, cannot have over an octet. And that's total electrons shared.
And NOF is hydrogen bonding, right?
That deals with hydrogen bonding. Correct. Resonance structure. What's a resonance structure?
Where you can switch the single and double bond. Or triple bond.
Correct. So like if you have SO4 where there's 2 double bonds, okay,
Like,
then the resonance structure, and you would, if it asked you to draw all the resonance structures, draw all the resonance structures, which means that you would do this.
Oh, that's dumb.
That's all the resonance structures for sulfate. Okay, based on formal charges and where the double bonds are. Okay, we wouldn't say that there's another one where we had the 2 doubles here and the 2 singles there. Okay, so.
we need to draw.
So is it, the resonance is just where you change, like where the
Yeah.
bonding is?
Uh-huh. And like carbonate's a good one. Carbonate, nitrate, where that double bond switches places
Yeah.
and those keeps moving around.
I'd like to see it in the real world.
Okay.
I'm trying to go through my calculator.
Visually, just something double.
For, I have 4 calculators.
All right. Gases. Gases are really fun. Okay. It appears that we see more gas questions in the multiple choice section because you can do simple calculations like P1V1 equals P2V2 without a calculator. All right. Also remember that under the same conditions, if you have 1 mole of a gas, they behave the same way. At the same temperature, they have the same speed. Okay. I'm sorry. Yeah. No, check that. If we're at the same temperature, who's faster? We're looking at gases at the same temperature. Which one's faster? Heavier ones or lighter ones? Lighter. Lighter gases are faster. Just because one gas is lighter and the other one's heavy, are the pressures different at that temperature? As long as you have the same number of particles, the pressure's the same. Okay. So even though it's moving fast, it's got a little mass and it's going to equal the same amount of pressure that the bigger one hits at that slower speed. No conditions at STP. 1 atmosphere. 273. Here's a fun one.
How many liters is that when you do it? Is it 22.4?
1 mole is equal to 22.4 liters. Okay. That's at STP. Okay. Holy cow. All right. Partial pressures. Okay. I like the question that was given on the mock exam, and then we saw it. Shoot. I thought maybe I gave it to you. I can't remember. But this trick right here, very good. Very easy. Okay. Make sure that you can determine partial pressures, and it seems like you always start with 1, you form 2. Okay, so you can look at that and be able to.
Is this what we talked about?
Yeah, put that next there. It's shown up 2 times in the last week, so I'm expecting to see it again. Okay. Make sure you do partial pressures. Make sure you understand the principles behind stoichiometry. Gases. Make sure you know how to do stoichiometry. Those 4 steps are really important. Limiting reactants. This is probably the one thing that freaks everybody out. Even though you're working with limiting reactants, and I see this drawing, or at least a diagram of this. All right, so you've got, let's say that we're looking at, we'll just use that sulfuric acid and barium hydroxide. Okay? If this is the limiting reactant, what ion, or how should this beaker look when the reaction's completed?
There will be leftover BA.
There'll be some BA in there. Actually, let's not draw circles. So they would be in circle form, so there'd be some BA.
And then there would be.
Well, water is assumed. You're not going to see water molecules.
And then, yeah, there would be a precipitate at the bottom of BA.
So are we going to see sulfate in this?
No.
No sulfate. All the sulfate's going to go away.
Yeah.
And all the hydrogen would go away.
All the hydrogen?
All the hydrogen. Since it's a limiting reactant, all of that's going to be used up because we have excess.
So there's BA floating around?
And OH, and
Will there be solid at the bottom?
better believe it.
Of the BA and the SO4 or what?
Got it. Solubility rules.
Okay, even if it is all universe, there's still be solid at the bottom.
Okay.
Mr. Craig?
Yeah.
But in the multiple choice question on the mock exam, it says excess NaCl, but the correct answer has Na.
Why? This is not the same reaction. Why?
No, I mean the other way around. The AgNO3 was the limiting reagent, reactant, whatever.
And there's NO3 in solution.
Yes.
Why?
Temperature is kept constant.
What's different about that reaction than this reaction? Big difference. Okay, ask your question again, Sam. Please ask it. Go ahead.
I just said that there's NO3 left.
Was it silver nitrate?
Yeah.
Okay, silver nitrate, and who else was it reacting with?
NaCl.
Sodium chloride. Okay, and we said that which one was the limiting reactant?
AgNO3.
Okay, so there's your LR. Okay. What should we expect to find in the beaker for this one?
Well,
What's going to be on the bottom?
AgCl.
Sodium chloride. Okay. What else should we expect to see? Will we see any Na?
Yes.
Will we see any chlorine?
Yes.
Will we see any silver? No. Will we see any nitrate?
Yeah.
Yes.
Why?
Solubility rules.
Why?
Here, all that sulfate is reacting with the barium that's in solution. If I have any barium, it's going to make a precipitate. What is the hydrogen doing? Which is different from these because both of these don't do something. That's the trick. See, we're making a lot of water molecules, and it's assumed that they're not going to show the water. So the difference is, okay, you got NO3 in here as well, but here we have a neutralization.
Because NO3 is reacting with the water. And then
Nitrate doesn't do anything. It's a spectator.
Well, yeah, it's just like chilling.
Yep, just along with sodium. Okay.
Hydroxide goes to water.
So,
That's it.
good pickup there, Sam. Nice. Okay. Not anymore. So if they ask you that, make sure you know the difference of what's being formed. And I would, Well, they probably did
Wait, so
tell
then
you,
why are there OH ions and not like 8?
because this is extra. All the hydrogen that was in solution got hooked up with the hydroxide. We got extra hydroxides. The reason why is because there's not enough hydrogen to react with it. Yep. So make sure you know, that's why I put on here limiting reactants, because I see that too many times where we automatically start to assume things.
Don't assume.
Don't assume, Sam. Please
Never
don't.
assume.
Lower the mistakes. Empirical formula, smallest whole number ratio. Okay. So make sure that you can do empirical formulas. If you cannot, make sure you can. Review that.
That's just converting the grams to moles, right?
We go to moles and then we look at ratios. Okay.
Ratios,
Ratio
yes.
of the moles.
Wait, you go grams, then you go to moles.
And then you find whatever the
Get it
smallest
to
one
moles.
is,
And then you get
divide
the
it all
answer, then you
that,
divide by
and
the
you-
smallest, right?
Smallest number of moles.
And then you'll get a whole number probably.
Yep.
Maybe not.
Yep. Now, there was a question on the mock that had something reacting with oxygen to form carbon dioxide and water, and it asked for what this was in empirical form, and I know that wasn't the complete reaction. Was there like a 2 here or something? It was like the first question right out of the gate. Was there a 2 here?
I can't.
On the multiple choice.
Multiple choice.
Actually, Andrews is right.
Wait, Andrew, you go back to do?
Yeah, he didn't want
Why?
Yeah.
He's got 3 weeks.
That's so unfair.
Okay, so on that first one, excess oxygen.
It didn't.
Oh, it didn't even give you. Oh, it did say carbon dioxide and water. Okay, it says equimolar. There you go, equimolar. What? Okay, what does equimolar mean?
Same amount of moles.
Same number of moles, equal moles. Okay, so if you have equal moles and a whole bunch of oxygen, well, we have 4 of those, we have 2 of those, we got 1 of those, we got 3 of those. So if we double it, double this, double that, now we got an even number of oxygen, we can work a lot easier that way. Okay, so you can find empirical formulas. Realize that this is what we need to focus on to help us get the formula. Okay.
Wait, I'm confused. How'd you confuse them?
So it should be an even number of carbon to hydrogen, I hope.
How do you know? Okay. Wait, but you don't know the very first thing.
That's what we're looking for. Yeah, if we have equal numbers of carbon dioxide and water, we have to have some empirical formula that's going to be based on
Why can't
whether,
it just be one?
because it gives us an odd number of oxygen, you can't balance it that way. So you have to be able to have legal balancing as well. And then empirical formula, does that deal with the smallest whole number or anything goes? Smallest. Empirical is anything goes. Make sure that if you see a chart or a graph or whatever this thing is, this is called a heating / curve / whatever. A good question could be asked is, all right, looking at this graph of water, where are we in the liquid phase? At what points are we in the liquid phase? Are we along between C and D? And here are your choices. Let's say C and D, B and C, D and E, all the above.
It tells you.
Oh, I see it now.
It's because he has it on his graph.
So which is correct? A, B, C, or D? Where is liquid at? Now, you're not going to be given that information. You should be able to look at this.
All the above.
Yes, all the above. So here's what we have. So this is for representing water. We have a solid. And if it's below 0, it is a solid. Okay? Water can exist as a solid. Okay? Then once it hits its melting point, then it stays at that same temperature, plateaus, so it now starts to melt. So you do have some water there. And then as we melt all the solids, then we add more heat, then the temperature goes up, still liquid. As it starts to get closer to its vaporization point, then we level off again at its boiling point until all the water's changed from a liquid to a gas, and then it takes off. Okay.
So there's none from E to F.
There is none, there should be no water or no liquid from E to F or from A to B. Okay. There might be a question asked. Here I have A, B, Z, and D. Which point represents the most water? Should be easy. Yeah, because that's all water there. This is part solid, part water. This is part water, part gas. Okay. So again, basic knowledge, just reading graphs and charts. Slow down. Ask yourself, what is this question really asking? Okay. All right. Reverse direction. If we remove energy, same thing happens. So we can take a gas and condense it down to a liquid. We can take that liquid and freeze it into a solid. Okay. So make sure that you check over those.
Stuff's in regular
Yeah. Make sure you know this phase diagram. Okay. What does that point right there represent?
The triple.
What does that mean? What does the triple point represent?
Gas, the liquid, and the solid all at the same time.
What does that mean?
And it's all happening
When does that
together.
happen?
Under high pressure.
High temperature and pressure.
It's at the temperature and pressure. So you have pressure here and temperature here. If I increase the pressure, okay, if I increase the pressure, then maybe at that same temperature, now I got a liquid. Okay? If I decrease the pressure enough, okay, then at that same temperature, maybe I have a gas.
Have you ever seen a triple point?
What-
I have never seen a triple
What, wait, we've seen that one.
We saw it in a video.
Yeah.
Have you ever seen it, Miller?
Do you know how to do it?
No.
Do you have the equipment here to do it?
No.
No.
Wait, so when the pressure and the temperature, what, how do you know?
When the, okay, so this is a chart versus pressure versus temperature. So if you have a certain point, okay, and I like the smart board for this. Let's say that we had this point right here for that particular.
She just
Like
said
the
I
smart
could.
board, what?
Love this smart board. At this particular temperature and that pressure, okay? So at that particular temperature and that pressure, water exists as a liquid. Here it can exist as a gas because I've lowered the pressure enough. Now, somebody explain to me, why is it a liquid here where it's a gas here?
Pressure.
Yeah, duh. But if it's a free response question.
Oh, because the pressure loosens the intermolecular forces.
Very good. So as we lower the pressure, the intermolecular forces become weaker. Therefore, it's easier for a liquid to change into a gas. Okay.
So
And then
it's
if we
just at a
strengthen it, then we can change that gas into a
certain- So
liquid.
it's just at a certain pressure and temperature?
Inter. Go ahead.
It's just at a certain temperature and pressure when that happens.
Yes. So it depends on the temperature and the pressure. So that's why this graph can move quite freely like that. So at a certain temperature, it could be either a solid, liquid, or gas, depending on which way we're going.
Yeah. And inter was for.
Okay. And obviously, if we cool the gas down,
Whoa.
okay, then we can start to go that way. Okay.
Wait, what's the one of the supercon?
Oh, okay. This point up here is supercritical. Sorry. The supercritical point is no, because you know that if we take a gas and we pressurize it, we can change it from a gas to a liquid. There's a certain point where no matter how much pressure you give it, it's still going to remain a gas. So that's the critical point, where that temperature is so high those particles keep moving that it won't be stationary enough or slow down enough to turn into a liquid.
Wait, can you go from a gas to a solid?
You can go from a gas to a solid, that's sublimation. That's an example of that is frost on your windows. So if you get the park outside, that's sublimating. That's going from a solid to a gas. You said a gas to a solid, didn't you? Yeah, an example of that is frost. Where you have liquid, you always have water vapor in the air.
Yeah.
Especially here in Indiana. So in the wintertime, when it gets below its dew point, then that water vapor finds cold surfaces and freezes. So it goes from a gas. Nobody's out there. Jack Frost isn't.
What's it called? What's the word for that called?
Sublimation.
Sublimation is when it goes from a solid to a gas.
Deposition,
What is it?
right? Deposition.
Yes, that's it. Thank you.
That was one of my flashcards.
There you go.
What's an
Okay.
example of a solid to a gas?
Solid to a gas, dry ice. Block of dry ice. Block of carbon dioxide, and it doesn't melt. It just goes straight to a gas.
That's sweet.
Do you have a bond length and stuff? Bond order?
No, I have.
Bond length, don't worry about. Bond order, don't worry about. Was that on the test?
It was in my book.
Okay.
Bond order is like Number of bonds divided by number of atoms.
Yeah, I've not seen a question like that on the exam. That's why I was hoping it wasn't on the
There's a
mock.
question on bond length too.
Bond angles, that's what,
Bond length.
okay, bond lengths we can talk about. Which is longer? A single bond, a double bond, or a triple bond?
Why'd you do that? You made me
Make
nervous.
it honest.
That's already easy enough question.
Yeah, so, and that's why it's harder to break a triple bond, not just because there's 3, but it's actually shorter. And again, Coulombic attractions draw those atoms closer together.
Well, it's
because they have
nicer
a
if we
higher-
actually have values for like the double bond, triple bond, not necessarily orders, but, oh, here we go.
The shorter the
So-
bond length, right?
A shorter bond length, so here's a double bond versus a single bond. So it must be because of the extra hydrogens that are actually bound there. So we have more of those bonds to break as well.
Wait, what'd you ask, Michelle?
He was asking why this was lower energy than something that had 6 total hydrogens on it. Because of those hydrogen bond, or the bonds between the carbon and hydrogen, those get broken. 6 of those. In addition to the ones.
Which is why they have, if you got double bond, it's a shorter bond length.
Correct.
Because it's strong.
Yeah. You got it.
Oh, this concepts kill me.
Concepts kill everybody.
Well, that's what you need to know for this test.
Yes.
I have most of them down.